So today, I'm going to introduce a set of very powerful tools that let us deal with one of the most fundamental questions in sort of describing, characterizing complex spatial and temporal systems. We've seen hints of some of the structure that sort of underlies information theory, but today I'm going to pull it out rather directly. So again, the way to think about this is, we have the Cover and Thomas Elements of Information Theory book, and that's partly measures of information, entropy, mutual information, conditional entropies, and another part, and probably the dominant part of the book, and maybe the most important technologically, are dealing with communication channels. So this week, we're going to more focus on the first side, measures of information, and introduce a very handy graphical technique called information diagrams that is, strictly speaking, not necessary from the mathematical analytical point of view, but is such a powerful intuition that you can actually solve many questions. Interestingly, it poses a number of sort of problems as you develop these information diagrams in different settings that actually leads you to sort of new ideas, interesting things. So the goal this week is to deepen our sense of information processing and what kinds of information there are. Just like last week, we sort of ended on talking about new things, sort of proxies for information storage like the excess entropy, transient information for synchronization, that kind of thing. Now we're going to basically look underneath and try to set up some more helpful tools as we deal with sort of arbitrary weight correlations in systems. So this is a key problem. How do you measure correlations in a system? And what do you mean by correlation? Very, very, very often what you see is people, in fact, the word correlation in physics is synonymous with a two-point relationship between variables you've picked. And there's a thing called a correlation function, which, in time, that take the Fourier transform of that, you get your power spectral density out. But it's all based on two-point statistics. If it was a spin system, probability of having upspin here, downspin here, upspin here, downspin here as a function of distance, but just two-point statistics. The dominant notion we have of correlation is just between 2 points in the system. And of course, if you're talking about two-point correlation, what you're forgetting is the state of the variables all in between the 2 points you're talking about. So there's a lot of statistics that you leave out, a lot of statistical properties, correlations, and structure you leave out. So in a sense, what I'm going to introduce today really brings us up the research frontier. This issue of what correlation is in a group of random variables is still very much a debate in the research frontier. It's certainly a general answer to that. So if I were just to give you a basket of random variables, you might have, at least at this point, some natural questions, like how much information do they share? So far, we've just talked about mutual information between two variables. And, it was used in information theory and communication theory to be the input and output of a channel, and mutual information was related to the channel utilization or capacity. But if I just give you a basket of random variables, how are they correlated? And what does it mean to have a three-way correlation, a four-way correlation? So the sciences and mathematical statistics have these ways of providing all these alternative models that just deal with single variables or pairwise statistics. So today I'm going to hint at what the directions of a general solution to this question. And that comes from generalizing Shannon's measure of information to what we call information measures, and then developing this graphical tool that lets us deal with what ends up being kind of a combinatorial explosion of all the different relationships you can have. But you'll see in 2, 3, and 4 variable cases, it's a very useful tool. Even 5 variable case, we can make a lot of progress. Okay, so now a little bit of review. So I'm going to step back to get a running start at this. So we just had a single random variable given by some distribution. Sort of the use paradigm for this is that I have a random variable sitting there. Could be a coin, could be some experiment I'm running. And I imagine that there's just one observable, and I keep coming back sampling it. In particular, the sampling process itself, how I'm accessing random variables IID. And in that setting, Shannon suggests that we use the entropy to measure the amount of surprise, the degree of randomness, the flatness of the distribution over possible events, and so on. Okay. Now, if we have two variables, say x and y, governed by their marginals and also by a joint distribution, of course, we have the joint entropy. Well, that's sort of understandable from the previous single variable case, because then we imagined that the joint two variables provide joint events. So we just have this one big distribution. We plug into the previous formula and we get this joint entropy. But then we have more interesting things talking about the relationship between variables, the uncertainty in x given y, the uncertainty y given x. We have this mutual information between the two, and then also this distance between the two distributions that govern the observables x and y. And then I introduced, if you recall, this diagram, mostly just as kind of a roadmap, because I had developed a whole bunch of different kinds of information identities, and this diagram lets us read those things off. So we have, think of this like a Venn diagram. This is the set of events x can take on, but then the size of it is actually the entropy of the distribution over those events. We can have another variable y in yellow here. The size of that is the entropy. Then the joint distribution is the whole thing here without double counting the overlap. We count the overlap just once. That's the joint entropy. We have the uncertainty in x given y. We think of that as sort of subtraction. We have x. We hack off the piece that's y. The remaining crescent is represents the conditional entropy, conditional uncertainty of x given y. And symmetrically, for y given x, we have y. We hack off the piece of x, and the yellow crescent is the conditional entropy of y given x. We have the mutual information. Again, now the intuition builds up. That's exactly the overlap. It's the size in a sort of event space of the overlap between the two different random variables, the sort of shared information. And then we have this distance metric, which is just the sum of the two outer crescents. Okay, so that's very nice. And then you can talk about how, you can see how the mutual information is, for example, h of x plus h of y minus the joint, right? If I have h of x plus h of y, well, I've actually overcounted the overlap here twice, and then I subtract off the joint. That leaves one copy of this shared area, which is the mutual information of x and y. So a lot of those identities, I mean, this is the easiest thing to remember. You don't have to hold the individual identities in your head. You just think about this and kind of go back and forth. And so again, we're talking about distributions, over x and y, joint distribution, marginal distributions. We're not having to carry around these bags of all these probability amplitudes. We just have this nice geometric picture based in terms of the scalar, and now it's a little more graphical in that it's a size of a set. Yeah?
So shouldn't that be x given complement of y and y given complement of x?
Yes, right. We'll get to that. I have to bring out, to talk about the generalization, I have to bring out the set theoretic analogy more directly. So we will do that in probably too much detail, but yeah, we'll get there, yeah. Okay, so is this, well, I kind of gave away the punchline. Is this just some sort of cute mnemonic shorthand for doing things? In fact, it's not. It's actually a hint that there's a great deal more structure underneath when we use information theory to describe processes and complex systems. Okay, so now start pushing ahead to three variables. So x, y, and z governed by this joint distribution over all three of them. So now let's think about what possible information quantities could there be. Well, again, we can think of this as a single triplet event, and therefore the joint entropy makes sense. We just plug that in. So that's kind of readily comes to mind. We have no trouble with that. But now, what set of conditional entropies do we have? We have all these possible questions we could ask. The uncertainty in x, so we have kind of the single variable conditional entropies and uncertainty x, y, and z, given that you know the complement of them, the other variables. We can look at the joint entropy in pairs, conditioned on the remaining variable, so uncertainty of the joint events x and y, given z, and so on. Okay, so suddenly, rather than just two conditional entropies, we have 6. Well, hints at how the complication is going to arise. We should expect this, right? I mean, It's not going to be a simple question. If I have a bunch of random variables, what are the relationships? There will be combinatorial possible ways of these things interacting. So sort of expect this. We've also worked a little bit with the conditional mutual information in a couple different settings. One was, for example, talking about the data processing inequality or Markov chains. We had this notion of shielding. So what's the mutual information between x and y, given we know z? And if it's a Markov chain, x goes to z, goes to y, z shields x from y. So if the variables were a Markov chain, this mutual information would be 0 given the intervening variable between them. So that makes some sense. It's just, you know, what we're familiar with, a two-variable mutual information, then conditioned on some third variable's information that might render them, say, independent, as in the case of the Markov chain. What about mutual information, though, for three variables? So this is the first interesting thing that we'll analyze. It takes a little while to get back to answering the question, but what is a three-way mutual information? So again, we're using the semicolons here. This is kind of democratically presented here. What does it mean for three things to share information? We developed some intuition for the two-variable mutual information. And then, I don't know, it makes sense that there's a distance between two variables, that d of x, y we had before. I don't know what it would mean for three. So this maybe is just an open question. What could that be? It was sort of all of the unshared information before, the outside crescents. So maybe so you could use analogies with a two-variable case to extend to three variables, and we're going to actually do that in a couple of situations. But generally, how are we going to deal with this? How are we going to visualize things? What sort of is there a similar kind of roadmap that we just had for the two-variable case? And then, of course, for n variables, we're now expecting this to get kind of messy. So the agenda for today is to introduce the mechanics of these information variables for arbitrary number of variables. Well, okay, now I say arbitrary number of variables. We're going to deal with 3 and 4 variable cases in some detail, develop some intuition. And then this information diagram is going to help us from having to write down tons of algebra, for example, to figure out what the information kind of relationships and identities are. Okay, so a few observations, and then we'll kind of get into a technical part of introducing this. So there's this kind of, maybe it's relabeling things initially, the Shannon information measures. And these are entropy of a variable, conditional entropies, mutual informations, and conditional mutual informations. So these are the things we're sort of interested in when we talk about Shannon information. And if you play around enough or look at the Venn diagram we had before, you can realize that all these information measures can be expressed as linear combinations of each other. So for example, in this case, linear combinations, I can take the information measures and express them as linear combinations of just entropies of sets. Okay, so the uncertainty in x given y is the marginal uncertainty of x minus the joint entropy between x and y. I'm just recalling some of those things. Mutual information, I can sum up the marginal entropies minus the joint entropy, and then this information metric was the sum of the marginal or conditional entropies. Sorry, conditional entropies, and so on. So obviously there are relationships between these things, and it turns out this is the general case, which means there's a lot more structure in these diagrams. So, in fact, think a little more about it. There's really no fundamental difference between entropy as a measure of uncertainty and the mutual information. There's this stuff out there. We'll just call it information. And you could even sort of, reformulate the way we introduced the entropy by defining it as a self-mutual information. Remember, this before was just this kind of property of mutual information I just introduced in passing. So in fact, I could just start with this mysterious quantity I, define this other function I use sometimes, h, just when we're looking at this shared information between a variable and itself. So self-mutual information. So there's really nothing fundamentally different about h and I. In fact, probably I should just change the notation at this point and just use one variable. I won't, but just say I, information. I can have I of x, which would have been past h of x. So there's really just this single quantity being referenced here. The notation comes from the use context they were introduced in, but it's not really fundamentally different. Okay, so this information measure, it turns out, now for some of the mathematical definitions and a theorem or two, these information measures form what's called a signed measure over event space. So let me say something a little bit about vocabulary here. The word measure is being used in two senses. Up until this point, I've been saying measure as if it's information quantity, that sense. But here, when I say measure, this is really a concept from measure theory, from probability theory. So I'll define what that means in this case. Okay, so the first thing we should do is we need some notation for the events that correspond to random variable. And I'll just put a tilde over the random variable to mean the set of events over which the random variable is defined. The sort of universal set of all possible events is just the union of these things. Okay, so that's kind of the universe of discourse. And just as a kind of a simple operation, I can develop what's called the sigma field. This comes out of measure theory, terminology from measure theory. But the basic idea is very simple. I take the sets of events and I take all possible unions, all possible intersections between the event sets and their complements. In other words, I'm trying to break these up as much as we can. It's as if it was a partition, and I was trying to refine a partition to get to the smallest elements that can be formed, smallest so-called atoms, subsets, okay? And then the measure itself is going to be this real valued function on the atoms. That's how we're going to define it. So the main mapping is here. We can go through and just define what this real valued number is that we're attaching to sets in the following way. Things familiar. So this measure, whatever it is, of the union of the event sets of two random variables, that number is going to be the joint entropy over the two. The sort of size, if you will, the measure of the X event set is going to be the entropy, the marginal entropy of X. Same thing for Y. Size of the Y set, according to mu, is just going to be the entropy of Y. When I take the size of the intersection, that's going to be the mutual information. So you should be thinking back to the previous diagram. I look at the set difference between X's event set and Y's event set. That's going to be the conditional entropy. Same thing the other way around. Conditional entropy of Y given X is going to be the opposite set subtraction. And then I have here this, I take the intersection of these two and then the complement of that, and that's going to be the sum of the conditional entropies, which is the distance measure d. And just to complete things for boundary conditions, the size of the null set that mu assigns is 0. Okay. So, and then this operation here, just to be clear, we can reformulate it down here in terms of intersections and complements of sets. So this is the mapping between, on one hand, well, first the kind of set theoretic manipulations we've seen already, and then we're adding a size to them, giving a measure to the sets, and then giving a meaning to that size, namely these various entropies, mutual informations, conditional entropies. So there's pretty much this kind of direct mapping. Anytime you write down some sort of information identity or some expression in terms of entropies and mutual informations, you can just almost do a syntactic replacement on what you wrote down, right? So H and I turn into this measure that we're looking for, comma, H of X comma Y. Think of that like a programming expression. What that means is union over the event set, semicolon is intersection, mutual information, right? And then bar, conditioning, is set subtraction. So this is not, the previous diagram is not some mere graphical help. It is that, but there's a much deeper level of structure in this. So just to say this mapping clearly, if I write out some information identity like this, mutual information is the sum of the marginals minus the joint, well, I just rewrite that using this to the mu of the intersection of X and Y events is equal to the measure of X plus the measure of Y minus the measure of the union of the two. And then down at the set theoretic level, we have this intersection is a union minus, yeah. Right, well, okay, that's a complement, right? So, wait a second. That should be, I have to think about that. That doesn't strike me as right. Sorry. Okay. So so why do this? Well, first of all, we're defining this over arbitrary numbers of variables. So there's at least the hope that we can go to n variables. Gives us some picture about how to extend these things. Remember, even for 3 variables, we didn't really know what that 3 variable mutual information was between x, y, and z. So maybe this will help with that. More directly, just makes explicit the structure. There are fewer degrees of freedom than one might imagine in playing with information quantities. It gives us a way of actually calculating things, reading off different kinds of identities in terms of if sometimes in some problems it's easier to do the calculation over the sets of events rather than information measures and vice versa. It's not always a benefit. In particular, there is this sort of combinatorial explosion in the information measures, but that's actually not its fault. But sometimes it's easier to work with this information measure view, sometimes it's not. And I said this before, it's in turning the crank, once we made the mechanism, the calculus of these information identities clear, sometimes natural, interesting questions fall out, and we can discover new kinds of thing, like new kinds of information, which will be sort of the topic today and then Thursday. So how are we going to do this? So I just want to go through the sort of main claim about this, mostly to give a tour of it without going through the proofs. So how are we going to define this information measure for n variables? Well, first thing is I'm going to just drop the tildes. You'll have to kind of know from context whether I'm talking about the random variable, the ith random variable, or the event set for the ith random variable. So I want to let W be some collection of these event sets, n of them. For n random variables, we have the universal set, okay, just like we had before, but we're just talking about 2 variables there. And then we have, so this is called the sigma field, this set of that's generated by this set of random variables, and you form that by all possible intersections of the random variable event sets or their complement. So, and these individual things are the atoms. There's an exponential number of these atoms as n grows, so it gets quite large. Yeah.
Just for intuition, is there any neat way of thinking about the elements of the universal set as like independent instances of the variables?
No, not independent, because what will be left over will be, it's almost like the atoms will be the sort of most highly conditioned pieces. So we'll give a bunch of...
There are subsets of that space. I'm talking about the elements of the space, right?
Let me push a little bit further, and then there'll be some diagrams, and we kind of point at things. You go, like, what does that mean? So, yeah. Yeah. Here I'm just turning the crank. I mean, I just kind of introduce things talking about 2 variables, and I'm just going to give the notation and lingo for n variables here. Right, so we have an exponential growing number of possible atoms, these residual sets. Think of all possible intersections. Remember back to when we made partitions and did a refined partition? The finest elements in the refined partition are the kind of an analog of these atoms here, except now it's not a consistent partition coming from a generating partition. It's any variables you want, just all possible set intersections. And then the number of sets, really the power set, is going to be 2 to the n. So we'll be talking about set of random variables. We find these elemental pieces called atoms, and then we also want to talk about subsets of that, which is called a power set. I have a set, the set of all possible subsets is called the power set. So that the size of the sigma field is doubly exponential in the number of variables. Again, this will be more concrete. Yeah, go ahead.
So it seems like you're including the intersections of the set with its complement of them. The two to the end.
Yeah, you can. I mean, it might be empty. Yeah. So this is just first turn the crank. Yeah. 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 Okay. So the main result is this. It's sort of notation heavy. It's really no different than what we talked about before, but basically all the setup, the mappings we made from sets and measures being the entropies and so on, and the structure of how we're taking marginal, joint, conditional, and mutual informations, that relates back to the set structure. So now we just imagine, to set this up, that we have three different subsets of random variables here, just to state the properties. Then generally, the idea is that if we union the variables in any one set, that's essentially the joint entropy. So I'm kind of adding a little bit of notation here, right? So this is the joint entropy of X, where X is in the set G. So this is all the variables in set G. Then we have the sort of union here of these variables in G and G prime. We look at the set difference, and that's the sort of this generalized conditional entropy measure of X given Y, where all the X's are picked from subset G and Y's are picked from subset G prime. Yeah. The W is just the set of variables. So variables x1 up to xn. So I have a set of n random variables. Or here what I mean actually is the event set associated with the random variable. I've dropped the twiddle because it just got too busy. So here when x shows up in a set theoretic, when x sub I is there in the context of a set, then it means the events associated with that random variable. When it shows up inside of an I or an H function, then it's a random variable. Okay. Anyway, you can sort of see what's going on here. I take this, basically all the random variables in G, union those, all the random variables in G prime, union those, and I look at the intersection, and then that corresponds to this mutual information between the variables in set G and the variables in set G prime. Right, so I have in my n variables, I have two subsets, G and G prime, and I'm asking what's the mutual information between those two sets. And then the final thing we need is a conditional mutual information, which just is the previous mutual information and then a set difference with a third random variable that comes from some other subset G double prime. So we get this mutual information, the variables in G with variables in G prime, conditioned on knowing the variables in G double prime there. Okay? So the claim is that this mapping is unique assignment, a unique measure on the event sets that's consistent with Shannon's information measures. Okay, so when it takes some time to prove that. Probably would take a lecture or so to really flesh it out. It's covered in the paper by Jung that was in the readings. But so much for that. Let's get back to thinking about how to work with this more concretely. And so it turns out that there are generalized Venn diagrams implicit in what we just set up. Crudely speaking, right, the area is going to be something like an information measure or an entropy. Conditioning is area removal, subtraction, mutual information is intersection. And a really important thing, and we'll do an example here, this measure can be negative. So for two variables, everything we've been working with so far, entropy, mutual information, has all been non-negative. Well, as soon as we move to 3 and more variables, it gets, let's say, more interesting. So some of these quantities we just defined implicitly in the previous slides, these measures are actually negative. So, however, if a set actually has 0 area, then the measure is 0 or 0 entropy. So at least there's that, but there's a slight sort of difference. And it's not, the measure setup is not introducing negativity. That's already in information theory when we start dealing with 3 and more variables. So we're going to have to maybe work a little bit to understand what that means. So just to go through all that formal notation explicitly again with a familiar case. So if we have 2 random variables, x and y, and their joint distribution, we have these 7 possible information measures. Just possible subsets I could pull out. So this is associated with the sigma field over the event sets for x and y. And then we have 3 atoms. These are like the elementary pieces. Right, the conditional entropies, h of y given x and h of x given y, and then the mutual information. So now with this in mind, we can just go back to this setup before. So that's x, that's y, right? The joint entropy is this piece plus this piece plus this piece. We don't double count. Now, right, the red part hacked out the yellow part, that's uncertainty in y, in x given y. Symmetrically for y given x. And then we have the mutual information, which is just the overlap. And then the 2 crescents are the distance again. So now, that's very familiar. We're going to do this for 3 variables. And the question is, what new thing do we get out of this? Turning the crank. Okay, so x, y, and z will be the 3 random variables. We have the joint distribution. And you could write out all possible, think of it just like with h's and i's and bars and commas and semicolons, what you could write out that was sort of a well-formed expression. So there's a lot of things to write out here, going from the marginals to the joint, and somewhere between we have the 3-way mutual information, the conditional mutual information, and so on, and conditional entropies like I wrote up before. Oh yeah, and then but it turns out there are just 7 atomic information measures, so there's a little bit of simplicity here. So this is what we have. Okay, rather than write this out, I mean, one could write all this stuff out in terms of information identities, best here. And the theorem shows that this will be a consistent representation of the information measures. Okay, so here's x, y, and now z is the new variable. And I put 3 circles here, and the way I place the circles, it allows each of the random variables to have all possible intersections and non-intersections with other random variables. So there's a piece of x, y, and z that doesn't overlap any other place. There's a piece that overlaps between x and z, between x and y, between z and y, and then there's a part that overlaps all 3. Okay, so now you can kind of imagine, like, what's this up here? What would this blue scalloped piece be? Well, that's h of z conditioned on x and conditioned on y. Okay, h of y conditioned on x and z, that's this piece here. Same thing for x. Okay, let's see. So what would this piece be here? Right, that's an intersection between z and x. That would be the mutual information, the 2 variable mutual information between x and z, 2 variable mutual information between z and y, 2 variable mutual information between x and y here. But what's this piece? It's a mutual information between z and x conditioned on x. The mutual information between x and z conditioned on y. All right? So it's very mechanical what we're doing here. But the set structure, just you can just read it off. There's not a whole lot of thinking when you do this, okay? And then this is the mystery quantity. What's that? We've defined it just by doing the Venn diagram, but now we actually have a candidate for what the 3-way mutual information is. It's some information measure that all 3 variables contribute to. Yeah?
I'm just wondering, is there an order of operations or anything on here? Because you have the conditional. Can you read that also as mutual information of y and z given x? Or
yes, right. Yeah, I keep wanting to find an actual grammar parsing for a parser on this. Yeah, so the question is, when I write down these symbols is there some sense of order operator precedence. Just like if I have x times y plus z times is evaluated first according to a compiler, right? So are there implicit parentheses here? So semicolon has precedence over bar. It groups them. So you could, in fact, it wouldn't be a bad idea if it's a little bit confusing to just go ahead and group with parentheses. It'd be perfectly consistent for me to put parentheses in, just to indicate that that's, same thing with comma. Comma has higher precedence than bar. That's implicit in all those definitions we did, but it could be made more explicit, yeah.
But it is different.
Yes, right. Right, and again, if you get confused, especially with like 4 and 5 variables, sometimes I just write in parentheses because I will forget. Or sometimes there'll be expressions you can write out that are a little bit ambiguous, so don't hesitate to add some notation to make that clear. Say again?
Yeah, I mean, one question. What's the difference between a semicolon and a comma?
The difference between a semicolon and what?
And a comma. I mean, they're both sort of joint, right? Joint probability, joint distribution.
Yeah, I think the honest answer to the difference between the semicolon and a comma is that that's the way Shannon introduced them. and it's kind of like there's a bit of overrepresentation. We have two symbols, I and H, that give the context of the interpretation of the symbols. So you could imagine developing a consistent notation where if I had I in front, then a comma over here would mean kind of that group of variables I'm doing the mutual information over. However, like you saw before, we can have mutual information between two variables and then other variables separated by commas here, sort of individually. So it is consistent. It's just, I'm not aware of anyone who's bothered to make this syntactically cleaner like that. But right, so this tends to mean union. It doesn't tend to mean in this mapping, which is now making these questions clear. This means union, and then the semicolon means intersection between the sets, the associated event sets. Yeah. So, but you could imagine, yeah. But now we have I and H's. That would be one thing to get rid of. I think you could just. You can pretty much tell what you're doing if I were to drop these based on the syntax internally. So there might be some confusing cases, but now, okay. So what good is this? Well, we can. Actually, this is a whole set of questions, right? This represents a large number of information identities that you can just read off, right? Right, the mutual information between X and Z is the three-way mutual information plus the mutual information between X and Z given Y. This quantity, this three-way mutual information, this new thing that we're going to probe a little bit, it's a little odd in some cases, but I just kind of described before, it's the information that all variables contribute to. It's also symmetric, right? There are different expansions of this. I can write this out in a couple different ways. I can have the mutual information between X and Z and subtract off this piece to get here. And similarly here, mutual information between Y and Z and subtract off this piece to get here, and so on. So suddenly, at least we can realize that whatever this three-way mutual information is, it's very symmetric. So it helps us maybe move a little step closer to understanding what it means. Yeah?
I have a question.
Yeah.
So what's the definition of the three-way mutual information in terms of the probability distributions of X, Y, Z?
Well, here. Just expand out, right? We know what the definition is of mutual information X and Y, and then we know what it is here, and we can just put in the conditioning, right? So here, the mutual information was usually a joint over the marginals. So now I have a joint conditioned on Z and marginals conditioned on Z. You just read this right off.
So it's not defined from the probability distribution, but
Oh, you can.
operation. Okay.
Well, no, I mean, here are three definitions that you can immediately translate back. What you're probably asking for is what is somehow, what does it look like altogether without going back to more familiar two-variable definitions, and we'll get to that. In fact, we're going to generalize, well, we're going to talk about what n-way mutual information could mean, and it turns out this is just one kind. So, and then I'll give you more explicit expressions in terms of probabilities. Okay, so now the important thing about this moving to three variables, in terms of, especially in terms of intuitions we've developed, we now have to unlearn something. Namely, that this three-way mutual information, unlike two-way mutual information and one variable entropy, can be negative. So this is the canonical example. Kober and Thomas go through this. We have x and y, both fair coins, Bernoulli random variables. They're independent of each other. They're just two separate coins. And then I'm going to form a third random variable, z, which is just sum mod 2 of x and y. Simple enough. This is actually how our friend, the random XOR process was made, except this was done in a sliding window. 2 coin flips. The third one at the next time is the sum mod 2 or XOR of that. Okay, so now we can calculate out what's going on. Well, by definition, x and y were independent fair coins, so their mutual information is 0. And so we can calculate this out. We just kind of expand until there's a quantity that you know. So we can look at the mutual information between x and y conditioned on z, the inputs conditioned on knowing the output. Well, just information identity, which we could read off before. So that's just the uncertainty in x given z minus the uncertainty in x given y and z. Well, if you think a little bit about the sum mod 2 operation, if I know the output and because of the sum, mod 2 loses information, I don't know what x is going to be. It doesn't determine x, so there's one bit of uncertainty in x, even if I know what the output of sum mod 2 is. However, if I know any two of the variables, in this case the output plus y, then I exactly know what x is. I can invert that sum mod 2 operation to figure out what x has to be to make z what it is. So we have one bit of mutual information. Okay, so first curious thing, they were independent, and then I gave you some additional information about them. I had an observable, which is sum mod 2, and that induces apparent correlation between them. Up here we didn't know that. Here we do. Okay, now the punchline is we can use the previous identities to look at the three-way mutual information. Well, one of those was just the two-way mutual information between x and y minus the two-way mutual information between x and y conditioned on z. We just plug in here 0 minus 1. So it's negative. So I'm not familiar with a nice narrative explanation for what it means to be negatively correlated. Our intuitions from conventional negative correlation don't quite apply. People are actually working on this right now. There's one response to 3 variable negative information measures and more variables to try to come up with a completely different mathematical framework where all the quantities are positive. And that has been, well, in short, not successful. Been very active last 3 or 4 years, not successful at all. In fact, a couple people thought they had it, and then just about a year ago, counterexamples were developed. So my inclination is just to work with it. So we will. Now what's this look like? So we just went through this calculation. Well, I just claim these information diagrams are helpful. Let's see what that looks like with the information diagram. So x, y, and z. Okay, so I just went through and calculated all of the quantities, right? So this is mutual information of x and z conditioned on y. That was 1. I went through and just calculated it out. And there's our minus 1 we just calculated. If I specify any two random variables, the third one is predictable. Specify any two random variables, the third one's predictable. Okay. So I just kind of filled in. So each one of the atoms here has its measure. So notice that we also know that the marginal of x, marginal entropy of y, and of z, those are 1. Just look at those 1 variables. They're Bernoulli. So is that consistent with it? Sure. 0 plus 1 minus 1 plus 1 is 1. Ditto everybody else here. Okay. We also noted that the two-way mutual informations are all 0. Pairwise, the variables are all independent. So what piece is that? Well, the mutual information between y and z is this shape right here. And notice 1 plus minus 1 is 0. Okay. So, oh, right. Yeah, so that's an indication, especially if you're doing problems, that the roadmap is very easy. You just kind of lay these things out. It's a little bit of crank turning to calculate the atomic values, information measure each of the values, but then you can answer a number of questions from that. So it's interesting how with a signed measure like this, a piece of the subdiagram will then indicate that one of the atoms, namely mutual information between x and z, could be 0. But somehow if you had more information, suddenly this breaks into a negative and a positive contribution. Okay, so now just to kind of exercise some of this, I mentioned just before a Markov chain. So you remember Markov chain, we denoted x goes to y goes to z, and there's this notion of shielding. If I fix y, z and x are independent, okay? And we express that this way. The consequence is that mutual information between x and y between x and z conditioned on y is 0. Okay, so question, how does that change our general 3-variable I diagram? Well, that's an atom, right? That's x and z conditioned on y. So that's this guy, and that should be 0. Actually, I did this backwards. Sorry. X and z, right? So mutual information between x and z would be this big piece here, and then I condition on y up here. I take that off. So that atom is this guy. So it's 0 for a Markov chain. Okay, so what I'm going to do is just go through and calculate, so identify the atoms here, and then change the diagram to reflect that this guy is 0. All right. And then here, so I just took y and kind of moved it down, and now that lower atom has disappeared. So we have just one less atom in the whole diagram. We have 6 other atoms in here. We had 7 before. So now this kind of takes on this kind of fan-fold kind of picture. In fact, sort of visually, if I say, oh, y shields z from x, it's sort of clear in the diagram. There is no overlap between x and z that doesn't go through y. Therefore, if I fix y, they can't see each other, right? The blue here shields them from each other. In addition, and this takes just a little more work, all of the remaining atoms, for when we have a Markov chain, all of these are positive. All the atoms are positive or 0. So that's nice. So in a Markov chain, for example, when we're dealing with the time series, we have a less complicated information diagram because of the shielding property. So this would be true of a Markov chain, for example. The state variables in a Markov chain obey this. And now you should imagine not just 3 of these, x1, x2, x3, but a whole chain, and this kind of infinite kind of lattice information diagram. And this is probably a better way to think about a chain like that. So the perfectly set theoretic equivalent to the previous one, but just sort of laid out. So here's y, and you can see how it shields z from x. And then this, you could imagine just drawing these humps off. So this is kind of hinting at how we're going to deal with time series and information in time series, is thinking this way. Although, there is a first cut at using the information diagrams that gives a lot of simplicity to think about processes. So rather than, so what we're going to do is now think about processes that we have, again, stationary if you like. We would, at first blush, we'd think, oh, we have this bi-infinite chain of random variables. This is an I diagram you don't want to write down. You can't write down. But instead what I'll do is just imagine the bi-infinite chain is broken into an aggregate random variable I call the past, and an aggregate random variable I call the future. So then, well, I can use a two-variable I diagram. Okay? So how are we going to do this? Well, the first thing is to sort of write down what the possible information measures are. Entropy of the past, entropy of the future, joint entropy of past and future, uncertainty of the future conditioned on the past, mutual information between the past and future, excess entropy, and so on. You can write these to whole things out. This might be a little mysterious. I don't know, what is this? Well, that's those two crescents, we know. But what is that thing? And then there are three atoms in this two-variable diagram. Uncertainty in the future given the past, uncertainty in the past given the future, and the mutual information between them. So you can probably already anticipate how simple the I diagram is going to be. So let's call that the future, entropy of the future, entropy of the past. This is this is like the predictive uncertainty, given that I'm looking at the past, conditioned on the past, I've seen the past, what's my uncertainty in the future? This one is maybe a little sort of acausal, but anyway, we're allowing ourselves to look at the big chain, so there we go. We can talk about the uncertainty in the past given the future. Here's the excess entropy, right? The mutual information between the past and the future, shared information. Now, what is this thing here that I noted before, right? This is in the diagram, whoops, too many animations here. If you remember before, we looked at the sum of these conditional entropies here, and that before was some kind of distance, right? So those outer wedges, or this quantity here, is the distance between the past and the future. So that's all very nice and intuitive. However, I'm kind of pulling the wool over your eyes because it's very suggestive and helpful, and it gives a little bit of insight. And Thursday, we're going to work on this process information diagram in some great detail and pull out some interesting information quantities. And then basically, next quarter, we're going to expand this quite a bit to talk about state-based models and past and future and so on, and it becomes extremely helpful, but at least even here. So one of the problems with how I'm presenting it to you is that is an entropy over an infinite number of random variables. It can be infinite. In fact, if the process is even a little bit stochastic, what's the information in realizations, semi-infinite realizations from even a slightly stochastic process? It's infinite. So those circles, I drew them finite. That's not correct. But it's also not helpful to have them extend off to infinity. So we have to be a little bit careful, and there's a way of dealing with. Really what I should have done is just talk about the block random variables and their entropies. Those will be finite for every finite L. And then, after you get some intuition about what's going on and the relationship between the quantities from the information diagram, then you sort of write out your proof with finite L's and then take the limits and so on. So it's kind of, you use the information diagram, get some intuition about what quantities you're working with, what the relationship is, but then when you write out, you want to make statements about what's going on, you work with block entropies and then take sort of the appropriate limits.
Does it matter that we have infinite entropies?
Yeah, because sometimes there are ways of answering questions where you are subtracting two infinities off and getting a finite answer, and that is just, I mean,
you can still define
we'll talk like that, but you really shouldn't do it, okay? Because there will be cases, I can tell you from firsthand experience, where you get completely confused. So, it's okay to, what I'm trying to say is, it's okay to use this as a first intuition, but that's all it's helping you do. And you really eventually have to write things out in terms and take limits and so on. So
even if you write them out as, because these are infinite sums, right, as probabilities and stuff, you wrote them out in terms of that, you still end up with
actually, a lot of the work we're going to be doing, we're not even going to worry about probability distributions anymore. So a lot of the conclusions we'll draw about how to measure structure in complex processes. We're not going to dip down to probability distributions necessarily. That's one of the benefits. We're now kind of staying up at this information level. Information is now our primitive, as opposed to a probability of an event. There will be problems where I actually want to go down to the word distribution or some transition matrix. We will do that, but this is so much handier. Again, just because we're using these scalar variables as proxies for the sort of flatness of these distributions, we can get a lot of mileage. And sometimes it just proves things at this level that apply to probability without ever having to deal with probabilities. So anyway, just kind of a heads up. We will be careful next quarter when we go through things to do this in most cases where it gets a little bit tricky. It's one of those slightly unsatisfying things where you have to be more careful and you work it all out and the result is exactly what you thought without doing it, but that's the way it goes. So just because there are those cases where it's confusing. But let me kind of drill down on this a little bit. Okay, so we have these possibly complicated quantities here, and I'm saying, well, okay, infinite futures, well, okay, we really should be thinking about maybe conditioning on a particular infinite past. That's fine, but then the entropy number here could be infinite if it was the semi-infinite future, so I'm going to look at the block uncertainty in the blocks given a past here. Well, but we know what this quantity is, actually. Basically, it is this conditional entropy of the L block conditioned on the past. Since we are conditioning on the infinite past, we basically are already at the level where we can do optimal prediction. And we know that when we do optimal prediction, our next symbol uncertainty is the entropy rate. So, and also through stationarity, every one of these L variables is that uncertain. So basically this block conditional uncertainty just grows as H mu L. So we do know some things here. So there's an infinity here, but this is exactly how it enters. So that's easy to deal with. And this has a consequence for the information diagram. Call it foliations, right? So here's the previous information diagram. We're talking about this quantity here. Right, so this now block entropy, I'm writing this down. This diagram is now actually correct because everything's finite. And this crescent here scales with H mu L. Actually, we'll talk about this the next quarter. You can also talk about retrodicting the past here. Actually, I got these backwards. These should be backwards. That's the past, that's the future. So just swap these two things. But they both scale as H mu L. But more sort of graphically, the way we can think about this, now just looking at one side here, is that block conditional entropy. As I increase L, from 1 to 2 to 3, I'm adding on a sliver, a certain amount of entropy or information measure that is exactly proportional to H mu. Right? I'm filling out this big block entropy thing here with these slices, and I know exactly how big they are. So there's a lot we can start to say here that's much more structured. Okay, well, so that's for 3 random variables, and I kind of stepped back and did the process information diagram just to show how this can work and that we know some things. What about for more than 3 variables? Well, it gets harder. We can do hyperspheres, or we have all sorts of ways of forming these Venn diagrams, right? If I have 4 variables, 4 sets, you have the Venn diagram as all possible intersections and overlaps. We have roughly an exponential growing number of areas or atoms, and you really can't do it for 4 or more variables in the plane. So here's one example, and there's a small industry of people who've sort of worked through possible Venn diagrams, right? We have some choices of the shape. Sometimes for some problems, one shape might be more useful than the other. So we have X, Y, and Z like before, 3 circles, and now I have a new variable W, and this sort of sausage kind of loops through. There's a piece of the sausage that's just in W itself, piece that overlaps just with Y, just with X, just with Z, pairwise overlaps, and so on. And if you go through and figure out this is a fair, represents all possible intersections of the sets and complements of the sets. That's too hard to work with. We worked with that for a while. It's just too messy. Turns out if you just get away from circles, something about symmetry. And if you're going to have a diagram, we just work with symmetry. So I'll show you some cases where we have 4 variables and use these ellipses in different ways. At least it's now nice and symmetric. It looks complicated, I admit, but there is a way to drive around these diagrams that makes more and more sense. So this will be the one that we'll use like this. Again, satisfies the same Venn diagram requirements before. Or if you were, say, you had your fancy 3D immersive cave room, you could also do this in 3 dimensions. So here we can go back to the individual variables being now spheres, not circles, but symmetric themselves. And then you have 4 intersecting spheres. I've been playing with this in our cave, and I haven't quite seen the benefit of this. But you can stick your head inside these things and count the number of atoms. And so there might be a simplification here. I mean, there would be a simplification if, for example, there's a Markov chain between these. Then we go back to 2 dimensions. So depending upon the property, sometimes you'll get a great simplification in these. But the general case, anyway, this just give you some idea of how this would go. Okay, so now I want to talk, just to finish up here, to use some of this to talk about various kinds of multivariable mutual information. In fact, mutual informations. Turns out there are a number of reasonable generalizations of what we mean by shared or common information between a set of random variables. And they sort of, the generalizations key off different interpretations of what we think the 2 variable mutual information means. So, so they're roughly, well, there are at least 3. There are certainly more, but I'm just going to talk about 3. There are 3 generalizations. The first one starts off thinking that the mutual information is the common information that all variables contribute to. That's the I, X, Y, Z that we just saw in the middle of all the Venn diagrams, okay? So this kind of this picture kind of starts from this identity in 2D. But there's also, if you remember, the mutual information can be framed as an information gain or relative entropy between a joint and the product of its marginals, right? The information gain between the joint and the product of its marginals. And that gave us some sense of mutual information was kind of measuring degree of dependence between X and Y. And then there's also another interpretation that starts with a different identity. Again, these are all equivalent with 2 variables, so it's really, this is the extra semantics we've added when we look at mutual information in different ways. So the joint entropy minus all this single variable unshared informations, the information that just the variables have alone, right? So it's the joint entropy minus that part of X that's not predicted by Y and that part of Y that's not predicted by X. So we're kind of cleaving out all the variables randomness that they generate themselves, and then thinking of that as the shared information. Okay, so what I'll do is go through these in order and talk about the n variable generalization. And pretty much the main way we'll make sense of this is using information diagrams, because it gets a little bit hairy. Again, we're trying to deal with, all these possible unions and intersections of variables and the complements and so on. So there's okay, so notation. I'm going to change the notation a little bit here because I want to talk about sets of random variables. In this case, you could think of this like a time series, but anyway, I'll just index these with a colon. 0 to n will be this set, 0 up to n minus 1. We have this sort of universal set over the indices, 0 up to n minus 1. A power set again, the set of all subsets of the index set here. If we have a subset in the power set here, the complement is just that set sort of minus the original set. So that's what A bar will indicate, just the complement. And then, again, if we have some subset of the index set, we'll have these indices I. And a real handy notation, I probably should have introduced it earlier, is just that I'll put the index subset as the subscript. So this is a collection of random variables, right, of those random variables I that are in that index subset. Rather than x1, x2, x3, that could be x sub 1 and 2. Okay, so just to get started here, let's do something familiar. So the joint entropy well, again, there's no mystery here, right? It's just we have the n random variables, we have a distribution over them, we just plug them into the P log P formula, and that's the joint entropy. But what I want to do is introduce this 4-variable I diagram. Okay, so for the n equal 4, x1, x2, x3, x4, and I've kind of straightened it out from the previous ellipse picture, but it's the same topologically as before. And then, so this is supposed to show us which atoms contribute to this number, to the joint entropy. In particular, they all contribute equally, and so I'm using the grayscale here to indicate the number of times an atom contributes to this quantity. Later on, I'm going to introduce other quantities where we have different weightings like this. So it's very democratic, uniform level of gray here. All of these atoms contribute equally to the joint entropy. Okay, so that's just to get familiar with the 4-variable I diagram. So, okay, so now here's the first generalization based on the notion of mutual information is the information all variables contribute to, that central piece in the I diagram. Okay, so what I'm going to do here, and I'll give a couple different definitions. So we're looking at now the mutual information of this block of random variables. And what I mean here implicitly is they're all separated by semicolons, right? But and then what I'm going to do is look at all of the subsets of random variables. In other words, A is an element in the power set of the universal set. And then based on the size of the set, I'm going to add or subtract them. So hold on for a bit. We'll see why we're doing that. It takes a while to justify this definition. But let's do it in the case of 3 variables here, 0, 1, and 2. So first I look at the sets that are all singletons. Size should be A minus 1. No, sorry, minus 0. Okay, so the entropies all come in with positive sign individually. And then the next step is to look at all the pairwise joint entropies here. But I subtract those off because that's size 2. And then I get up to 3 variables, all of them in this 3-variable set, and I add that. So the signs are alternating here. So that's what this means. Now, what you should imagine the exercise is you go back to the 3-variable I diagram and go through all the atoms and count them up this way. You put a 1 in all the individual variables, a 1 in the joints for and then subtract off a 1 for wherever there's a joint piece, and then add in a 3-way. And what you should find is that this definition uniquely captures I of x, y, z, that central atom. Not obvious, but you can go through the diagram. Convince yourself. There's another way to look at this, essentially equivalent. We can look at the joint entropy minus the mutual information between the variables in a subset conditioned on knowing the variables in the complement of the subset. So what I mean here by this notation, just to kind of spell it out, is if I had 5 variables, 0 through 4, one term up there would be x, 1, 2, and 3, their mutual information, conditioned on knowing x0 and x2. So this, or if I had 3 random variables, well, it could also be a subset of the 5 random variables. I could have the singleton here conditioned on variable 1, conditioned on variables 0 and 2. So that would be a conditional entropy. Okay, so again, you have to, you look at this and you should think, okay, what set theoretic accounting am I doing on my I diagram? The net result is, without going through, it's slightly tedious, is that both of those definitions uniquely pick out that 4-way shared atom. So at least we have now explicit expressions for what this is, right? I can go back to those different definitions and go back to calculating with distributions and so on, right? Those previous 2 definitions, I can rewrite those. But, you know, hopefully the benefit is we could stay at this level as long as possible before we pull out a probability distribution and have to calculate things. Okay, so again, what are the properties of this particular generalization? Again, it's common information to which all variables, or in this case, all 4 variables contribute. It can be negative, as we showed before for the n equal 3 case. I would say it's kind of hard to anticipate ahead of time in a given problem whether this is going to be positive or negative. I have yet to develop an intuition for that. Many of these things simplify in a time series case, which we're going to deal with on Thursday. And the other curious thing is that if any two of the variables are independent, the entire sum, the entire mutual information goes to 0. So it's a little bit sensitive, right? Yeah. Okay, so that's the first generalization, and I think it's the front runner in terms of what we would mean by multivariate mutual information. The other generalization goes back to this relative entropy or information gain notion where you compare a joint to its marginals, right? So this is the expression here for what we call the total correlation. It's also been called the multi-information. I don't like that term. So total correlation. Even the word correlation here makes a little bit of sense because it's sort of comparing individual random variables to the joint, kind of like pairwise statistics before. You can try to convince yourself, maybe you can almost sort of see that. Since this is log of a ratio, it's really the difference between two logs. So we have the joint entropy here shows up negatively, and then we just sum up the individual marginal entropies over atoms of size 1. So just sort of using the same notation. And then here's the 4-variable I diagram. So again, what it's doing is we have the joint entropy here, which would be all the elements, and then I subtract off the individual marginals. It takes a little while to do accounting. So there are different counts here. In fact, I've got that on the next slide. So if you go through and look at the terms in the sum, there are atoms that have just one contribution to the sum, some that are doubly counted, and then others that are triply counted. So this particular generalization, it tends to overcount correlations, multiply count them. It gives you kind of a wrong, too high an estimate of how correlated the set of random variables is. Which sort of makes sense because it's just the joint versus the more individuals. There could be 3-way and 4-way correlations that contribute to total correlation, well, shared information or not. It's positive though, so that's nice. I mean, it should say non-negative. Also, if any pair of random variables, or I should say if one random variable is independent of all the other individually, then it doesn't really contribute to this total correlation number. So there's this additional random variable, it's not correlating anything, it doesn't change that. So at least that sort of makes some sense. But the main concern here is it tends to really overweight certain.
But then this reduces to I in two.
Yes, right. All of these go back to, right, so.
These are all I, but as we expand to multiple
Right,
dimensions,
right.
They got different dimensions.
Exactly, right. So the way to think about it is, I mean, it's not so much that one is correct. These are tools, and the issue is, what's your question? And they're answers to different questions.
They're different measures that have the same value in
Two
dimensions.
Right. They all come down. But we have these ways of, I mean, maybe in some way what we're doing when we go to more variables, we're realizing we had a lot of extra baggage we brought to the 2-variable case that we're kind of conflating. And now they're really very different kinds of questions that we're asking, could be asking. And then we have these different ways of measuring that. Okay, then there's the third one. Is called the bound information, and we're going to use this a lot on Thursday. It's a nice, interesting quantity for time series, but not in the time context. What it does is it's easiest to kind of explain up here with the I diagram. So it's sort of like the total correlation, except the atoms that are positive are kind of just ones. It doesn't overcount. Or the other way to think about it, it's the joint entropy, everything, minus those atoms that are just unto the individual variables themselves. Right? So sort of the locally generated information. It's not shared with anybody else, gets subtracted off. So it's what's left over. So in the temporal setting, we call this the bound information. So joint entropy minus the sort of individual all the information generated, the X4 generates on its own and that is not correlated with the other variables. All the information X3 generates that is not correlated with the other variables, and so on. So it's also positive. That's nice, and it also has the same property that if a given random variable is independent of all the others, then it doesn't change. This quantity, in some sense, doesn't participate. So those are three different kinds of mutual information. Like on Thursday, they really are answers to different questions, but very helpful in the time series context. The bound information is interesting because the way we're going to use it is, we'll think of it, we're going to decompose the entropy rate, which we think of as the spontaneous amount of information generated in the present moment, and the different components of it. Some of the spontaneously generated information is forgotten, but some is remembered, and that's going to be the bound information in the time series setting. People make the analogy with there are random events when you're listening to musical composition. For example, the composer just decides to change the key. That's a random thing that gets done at one moment in time, but it has an effect for the rest of the piece. So we'll come back to that use of it. But just to sort of finish up here, some things we will end up using. There are other kinds of multivariate informations. I'll just highlight a couple of them. One is the residual entropy, call it the anti-mutual information. We already kind of saw it before, it's the information that the variables generate on their own that's not correlated with anybody else. Well, I could just write it joint minus the binding information, right? The binding information is all the white stuff, and I subtract that off from the joint, which is everything, and I get these pieces, right? So you have a collection of random variables, they're generating stuff, some fraction of that is not correlated with anybody else. So that's the residual entropy, and this is going to be important in the time series context I just mentioned. Information in individual variables that's not shared in any way, hence anti-mutual information. And then there's a local exogenous information. We're kind of running out of vocabulary here, but these different problem contexts are actually helpful. You might call this varied mutual information. It's the information in each variable that only comes from its peers and it's not generated by itself. It's kind of complementary to the residual. So here, the easiest expression is the bound information plus the total correlation. And here's the information tableau. It sort of takes down the counts from the total correlation all by one. So, this discounts for the randomness produced locally. So again, you can kind of see how these would be answers to different kind of questions. You want to see how much a variable is contributing to a process, or maybe is not contributing to a process. So I can't really imagine starting, we work with these things, but these information diagrams are critical to kind of extending these ideas and working with them in a constructive way. Despite my caveats in the time series case with things blowing up, still very, very helpful. So that's it for today. Next lecture is the last, so I'm going to talk about these ideas applied in the time series setting to get back to this entropy rate decomposition, and then part of the lecture will be about what's coming up in the spring, which is going to be yet another shift. We're very close to, although it's a quick introduction to this kind of more modern information theory, we've at least haven't, by Thursday we will have exhausted most of the tools that are there. Certainly they can be enriched and applied to many different settings. Hopefully this will happen in some of your projects. But there are also some issues and criticisms. Certain kinds of questions we can't address, even with all these extensions and all this kind of enriching our notion of that there are different kinds of information. So that'll be it for today.